Okay, so here we have web sign 6E. Is this 13? It's one of them. Okay, so mass 1 is equal to 16.5 kilograms. A 16.5 kilogram object and an 11 kilogram object are suspended, joined by a cord that passes over a pulley with a radius of 10 centimeters. Mass of 3 kilograms. The cord has a negligible mass and does not slip on the pulley. The pulley rotates on its axis without friction. The objects start from rest 3 meters apart. Treating the pulley as uniform gets determine the speed to two objects as they pass each other. Okay. 1 is equal to 2 is equal to 11. Okay, so this was the rotational unit, so obviously we're going to have to look at rotational things. Now, okay, so immediately M1 is greater than M2, so we're going to be rotating this way, right? Yeah. So the distance we're going to be going is 3 meters because we want to see as they pass each other. So that'll help us. Let's get our formulas. Okay, so we are going to be using the kinetic energy of the system is equal to the potential energy of the system. And we use is that, what letter is that? It's not W. It's not, I don't remember what the letter is called. Okay. Yeah, it's not alpha. I literally don't remember. Okay, it means angular velocity though. Okay. So we got the I is equal to angular velocity is equal to the mass times gravity of the system. Okay, because energy is conserved. But we need more pieces to it. So, because we have 3 things in this. We have this mass, then we have the actual rotating disc. So we actually need to elaborate this onto 1/2 m1 v squared plus m2 v squared. Now these are the kinetic energies of each individual mass times the respective velocity, and the velocity will be the same. Their mass is going to be different, but the velocity has to be the same. It's like, say there wasn't a pulley here, and it was just 2 masses connected to each other. Say this is 1, this is 2. If I have like a car pulling M1, it's pulling the whole system. So M1, while it might be closer to the car, it has to be going the same speed as M2, assuming that the rope is taut. But that's what we're going to assume, the rope is taut. Like how it is in the pulley system up here. So if I pull this mass at a speed, it might take a second for M2 to reach the same speed to make the rope taut. But once we do, they're going to move at the same speed, and that same is true for on the pulley system. When one starts moving, the other's going to have to move at the same speed because they're connected to the same rope. Okay, so we got the individual masses. Now we have the actual rotating pulley to go to the change in height, because that's what potential energy is, actually change in height, and the actual mass of the system, seeing as they're on opposite sides, and they're gonna naturally move in the direction where the heavier mass is this way, unless acted upon by different. That's a whole other thing. We're not gonna get into that because that's not what we're asking. We're asking just how, with the speed that's going to go down, the speed that's going to go up. Okay, did I finish writing that? No. Times gravity. Okay. Boom, bang. Just the 2 over there, not the change in height. Okay, we're still done with substitution though. What's the W? I don't remember what the W is. That's equal to velocity over radius, because we need this is angular velocity, and we're trying to convert to linear. And we get, I'm gonna change the color. M1v2, or not, m1v squared plus m2v squared plus, this is v squared r squared. Yeah, I'll wait this step. Okay, now this is v squared r squared because this is what w equals. We got w squared, so w squared would have to equal that. It's not w. I know it's not w. I don't remember what the letter name for the letter is. I'm sorry. Equals change in h m1, yeah, m1 minus m2 g, and then there's one more step. We have to change what the I, when the universal value is mr squared of a rotating system, and then boom. We'd love to see that. I'll get rid of more unnecessary variables. Let's change in h. So I'm not really doing any physics right now. I'm just canceling my variables. It's basically just algebra right now. We love algebra. R's are gone. Now I can pull out the velocity squared and make this thing look a little bit nicer before I plug in all my stuff. So we got v squared times m1 plus m2. So 1/2. Isn't it? Yeah. Okay. This big M is the mass of the pole here. Yeah, it's the mass of the pole. Sorry, I just my stomach. Again, this is all just algebra to this point. I'm just doing this in one step. I'm dividing by this and taking the square root at the same time. In case there was any confusion how I got here so fast. And then, yep, m1 plus m2 plus 1/2 mass of the plate. This is all into the square root, by the way. I did not really show that well. Okay, so what I did, I set the kinetic energy of the system equal to the potential energy. I then plugged in for each part that would have potential energy, meaning this mass, and the entire, not the entire system, and the pulley system as a whole. Potential energy, I subtracted the masses because they're on different sides, and well, no, it's not really. If you were to cancel them out, what the mass would actually be equal to, times the gravity, which is obviously what's going to be causing this rotation, times the change in height, and that's a key component for potential energy as a whole. Continue to substitute for my actual values of I. No, it's not W. I don't remember. For that value until we got here, the radius squared cancels. Then we got all three velocities on one side. We took it, put it outside the parentheses, then divided by a whole, took the square root, and that's where we are. So now let's go back to the question and look at what we actually need. So we have our masses. Then we have the distance we are. This 3 meters right now. Let me clear this up. And use a darker color than green. This distance right here, that's gonna be our change in height. And then we have our other mass. That's the mass of our disk. So our velocity will be equal to change in height, which is 3. And I'm gonna call this is gonna be positive for me, just so because our velocity is under a root, so it's gonna have to be positive. So I'm just gonna say this is our positive direction. 3. Let me use units actually. Three meters times M1 was 16, I believe. Yeah, 16.5. Minus M2, which is 11 kilograms. And this is times our gravity, which is which is always not, well, these were on Earth, so it's always 9.8 newtons per kilogram. We're assuming we're on the surface, but that wasn't this unit. So over M1 again was 16.5 kilograms plus the 11.0 kilograms. I really hope it's 11.0, right? Yeah. And then times the mass of the half the mass of the rotating the disc is what it's called. Okay, it's just called the pulley. Gotcha. And then you do you plug in your values, I guess, and then you just get 2.36 meters per second. And then it makes sense to not be crazily fast. I mean, while there is a 5.5 kilogram difference, like it's like 13 pounds. It's only traveling 3 meters, so it doesn't have a lot of time to accelerate. I guess the reason I guess this you could say this value would be somewhat higher is because again that difference is, it's like the weight of a baby, I guess. It's like a 4-month-old actually. Never mind. But like, just like check your answer sometimes. When I first did this problem, when I first tried it, at least I thought this one was gonna take forever, because I saw 3 different parts to the system, and I was like, yeah, I'm not doing that. Well, you know, like, it didn't really, I kind of wrote big, but like, this could be one line. 1, 2, 3, 4. That could probably condense where it's still at 3. It's like 5 lines of just like algebra trying to get other stuff, and then all you do is plug it in, because you're given all the information you need. It's not like, can you just solve for radians a second given, and you have to like use your fraction with 2 pi, and it's nothing like that, because all you're solving for is not meters per second, is your velocity. So yeah. And like again, it's just as simple as setting your energies equal, your kinetic energy equal to potential energy. If you can do that, and don't forget to substitute your 1/2 mr squared times v squared over r squared, which is the universal one, which I've done multiple times. I've forgotten to do that, so I got one like this wrong on our test. If you break it down to small pieces, it's like, what am I looking for? Okay, now what can I use to get there? And all of a sudden you're solving it, and you're like, wow, I'm smarter than I thought I was. So just really believe in yourself, and when one thing doesn't work out, just try something else.